Alright, in this video we're just going to do an example of solving a second order differential equation. You can be suspicious that we're going to get some complex roots because that's what I promised in the last video. So here my characteristic equation would be s squared plus 2s plus 5 equals 0. Remember, we just replaced the second derivative with s squared, the first derivative with s, and the y just becomes a 1. Okay. So if I wanted to solve this equation, it does not factor, big surprise. So I'm going to use the quadratic formula. So s is going to be the opposite of 2 plus or minus the square root of 2 squared, which is 4, minus 4 times 1 times 5 all over 2 times 1. So that's negative 2 plus or minus the square root of 4 minus 20 all over 2. That is negative 2 plus or minus the square root of negative 16 all over 2. That is negative 2 plus or minus 4i over 2. If I factor out a 2 on top, that's 2 times negative 1 plus or minus 2i all over 2, and I can cancel. And so I get negative 1 plus or minus 2i. Okay. So I'm going to pick one of those roots. I'm going to pick s equals negative 1 plus 2i, and then I can say a complex solution is going to be e to the negative 1 plus 2i times t, which would be e to the negative t times e to the 2it, and I can apply Euler's formula to this imaginary part. So e to the negative t times cosine of 2t plus I times sine of 2t. Alright, so if I distribute the e to the negative t, that's e to the negative t times cosine 2t plus I times e to the negative t times sine of 2t. This is the real part. This, without the I, is the imaginary part. And my general solution is an arbitrary linear combination of these two. So my general real valued solution is going to be y equals a copies of e to the negative t cosine 2t plus b copies of e to the negative t times sine of 2t. Not too bad. A and b here are, of course, just arbitrary coefficients. Just a reminder, in proofs, I expect you to identify every symbol that you use. When you're writing general solutions, it's pretty much understood that if you introduce coefficients in front of things, those are arbitrary numbers. If you want to explicitly write a and b are real numbers, totally fine to do that. Okay, excellent. So in the next case, we're going to look at the third possibility that we have real roots to the characteristic equation, but repeated.